So we are going to be looking at the normal distribution, right? The normal distribution is a different type of probability distribution. So far, we've looked at the binomial distribution, okay? The binomial distribution roughly has that kind of hill sort of shape, sometimes with a tail at one end, sometimes with a tail at the other end. But the thing with the binomial distribution was that there was, what were the four things for a binomial distribution? Two outcomes.
Either true or false or something.
Okay, two outcomes, fixed number of trials, independent, and two outcomes. So the two outcomes is interesting because the two outcomes means that something is discrete. Okay, it means that there's only a particular kind of thing that it can be. It can either be yes or no. It can be red or blue. It can be success or fail. And the normal distribution does something that is different. Okay, the normal distribution is to do with things that are continuous. Can you think of something that is continuous for me? Height. Height is the most classic one we would say for height. Height is a continuous variable. Any other things? Speed. Time. Anything that's measured with time. There's so many things that could be continuous. And you can't use binomial for something that is continuous because of what we've just talked about, that idea of there's only two outcomes. So the normal distribution is going to be a little bit different. What we'll start off by doing is thinking about the characteristics of the normal distribution. What is the normal distribution? What does it look like? Then we're going to start learning about how to find probabilities, which we'll be using our calculator. Then we will be finding things where we don't know about the mean or the standard deviation. And then we'll be doing some things where we take a binomial problem and we change it into a normal problem. And then lesson 4 probably will be dedicated to doing hypothesis testing, okay? So let's kick off and think about the normal distribution. So the normal distribution, what does it look like? The following shows what the probability distribution might look like for a random variable x, if x is the height of a randomly chosen person. So what we have here is we have this kind of shape where there's a big peak, and this big peak happens at about 180 centimeters. What do you think 180 centimeters roughly for height do we think it means? It's like the average height, okay? Maybe for this particular group of people, the average height is 180 centimeters. And that's why there's this big bump here, because there's a high probability of someone having the average height. You do get some people who are very, very tall. You do get a very few people who are exceptionally tall, and the same is true on the other end here. So let's just read what we've written. We expect this bell curve shape, and it's a bell curve because it's meant to look like a bell. I'm sure you've seen like the bell, or any kind of bell shape, whatever, where we're most likely to pick someone with a height of around the mean of 180, and the probability diminishes. It goes down symmetrically either side of the mean. Okay, many things in real life have this normal distribution, and it's symmetrical. I'm going to probably say that it's symmetrical about 5 or 6 times in today's lesson. It is symmetrical, so you have to keep that bearing in mind. A variable with this kind of distribution is said to have a normal distribution. For normal distributions, we tend to draw the y-axis at the mean for symmetry. So here we've got the y-axis at the end. What we probably usually do is we will put the y-axis in the middle, where the middle is actually the value of the mean. Okay? There's a few more things I need to tell you about this normal distribution. Why is it not going on to the next page? So here are some examples of some normal distributions. Okay? So this first one that I've got, the blue curve, has a mean of 0, and because these have been printed in black and white, you may need to label which one is which on yours. So this is number 1, and you'll notice that it has got a mean of 0, so you can see that its big peak occurs at 0. And you can also see for the red one and the orange one here that they all have got a peak that is at 0. That is the average for that particular data. I don't know what that data might have been, but on average, it came out as a 0. The thing that is different, though, is this sigma squared. What does sigma squared mean? The variance, okay? And we're actually going to be using what you've seen on your calculator. We won't be using variance to type in. We will be typing in the square root of that. We'll be typing in the standard deviation. So just have a quick look. You've got the blue one, the red one, and the orange one. What does it appear that the variance is doing to the shape of that bell-shaped curve? It's making it wider. The larger the variance, the wider the curve. Now let's just try and think about why that is, okay? Imagine that we were talking about something that has a large standard deviation. What does that mean if something has a large standard deviation? It means it's more spread out, doesn't it? So that's why this orange one here, which has got a large standard deviation, is really flat and spread out. It probably means that it's more likely that you get someone who is super tall or super short, okay? Whereas this blue one that we've got here, which has got a very low standard deviation or low variance, it's really tightly squished in together. So the only other one that we need to have a look at is the green one. What's changed about the green one to the other ones? Yeah, the mean is -2, so we can see that's shifted it so that the central peak is at -2, but it is still symmetrical about that central peak. And it's got a standard deviation that's somewhere in between the red one and the blue one. Can you see how the standard deviation fits between the red one and the blue one? Yeah, you can just see it's kind of the way it's spread out is somewhere in between those things that we've got. This bit that I've got written at the bottom is really, really important because we need to understand how these things are written. So it says we can set the mean mu and the standard deviation sigma of the normal distribution. Quick side note there, mean, mu is the Greek letter for the letter M, so mean, and sigma is the Greek letter for the letter S, so standard deviation. So it does actually fit, they're not random letters that have been picked. So if a random variable x is normally distributed, we write this. Now I'm actually just going to rewrite what it says. I would say that the random variable x is distributed normally with a mean mu and a variance of sigma squared. The reason we write sigma squared is because often we just want to pull out what the value of sigma is because that's the thing that we'll use in our calculator, okay? If they ever ask you to write down how is something distributed, this is the kind of thing that they're asking for you to do, even if you've got some unknown things that exist in there, okay? So some facts about the normal distribution. For a normal distribution to be used, the variable has to be continuous, okay? It has to be something that is continuous, which is why we've talked so far about height, why we've talked about weight, why we've talked about the amount of time that something would take. If we wanted to find the probability between I wanted to talk about this bit first. With a discrete variable, all of the probabilities had to add up to 1, okay? We knew that all of the probabilities of something occurring had to add up to 1. So for this continuous variable, we similarly want the area underneath this graph to be 1. It's the same kind of idea, apart from now we're thinking about the amount of area that there is under this graph to be 1. Yes?
Is there like you can choose whatever values you want it to be in between, and all of that always has to be under like 1?
Yes. So what you will be able to do on your calculators is if they told you about something to do with what the average height is and what the standard deviation is, you could calculate by finding out what is the area between 170 and 190. But you don't have to use integration for this, okay? These are all values that have been generated through integration and are stored in your calculator. You're never going to be doing integration for this. So if you wanted to find out the probability that a person's height was in between 170 and 190, we would just find the area between them, and this is what it would look like on the graph here. What do you notice about the shape of this bit that's been drawn here? It's symmetrical, and the reason it is symmetrical is because the distance between 170 in the mean and 180 and 190 in the mean is just 10. So what can you tell me about this area? Good, it's the same as this area that we've got over here. That logic that we have, you're going to need to apply that logic, even though you think, oh, I'll be able to get it out of my calculator. There are times when you can't get it from your calculator, and that's when you have an unknown mean or an unknown standard deviation. So if we ever wanted to, would we ever want to find out the probability that x is equal to 200, for example? Well, no, you wouldn't ever want to do that because height is continuous. If I'm saying what's the probability that someone is exactly 200 centimeters, it is infinitesimally small. So it's not really a probability. Now, the reason that's true is you might say, does anyone know how tall they are in centimeters? 172, okay? But if I measured Rayhan accurately, he might be 172.3 centimeters. So actually, if I said, oh, I'm going to find out the probability that he's 172.3, I would then be like, oh, well, actually, he's actually 172.31. So there's no point. Every single time, you can keep making it more and more accurate so that if you were ever trying to find out the probability that x was equal to 200, it's basically non-existent because it's such a small thing. So we'll always be looking at things like this that are ranges of things instead. And I've just put a side note at the bottom. You might wonder then what the y-axis actually is. It is the probability density. So the probability per unit centimetre in this particular case. So this is the same kind of idea when we've done histograms. You know, when we've had like frequency density, it's that same kind of idea where the y value was the frequency density for the area under the graph giving you the frequency. So in this case, that's why we're using f of x rather than p of x, because we're not actually saying it's the probability, we're saying it's the density of the probability. But you don't need to know this, it's just a little extra bit for us to think about. Okay, I've got a few more facts that I need to tell you about the normal distribution before we can even get close to doing any questions here. I've printed this all though, so you've got it for your notes to look over. This is something that is like sneakily been added into the specification, and we haven't seen it been tested yet. So I think it's the kind of thing that they might be interested to test. It says that the curve has got points of inflection, which are one standard deviation from the mean. So if the mean was mu, there would be a point of inflection at mu plus sigma, and if there was, there would be another point of inflection at the standard deviation below the mean as well. What do we mean, point of inflection?
Point at which the grader changes direction.
Yeah, where it's changing direction. So here it looks like we're sort of swerving to the left. Here, if we imagine when we're driving a car, it's where the car steering wheel would be straight, and then we're swerving to the right, and then here we're going completely straight, and then here we're swerving to the left. So this little fact that we've got here, when you do your flashcards and things that you're revising, that's going to need to go on a flashcard, because I haven't seen it come up. I think there's one question in the exercise book. Yeah, it's 1 mark. But that's 1 mark that might be the difference between you getting a B and an A. So make sure that you have these kinds of facts memorized, okay? It has points of inflection there. This is also another bit of stuff that is just some information that you're going to need to have on a flashcard and that needs to be memorized as well. We have something called the 68, 95, 99.7 rule. I mean, it's not exactly the snappiest of rules to remember. And it's used to remember the percentage of data that is within 1, 2, and 3, so 1, 2, and 3 standard deviations from the mean respectively. And this needs to be memorized. So what we're actually saying here is that 68% of the data is within 1 standard deviation of the mean. So most of the data that you'll be looking at, if we're talking about the heights of all of the students in Morpeth School, if we worked out the average and if we worked out the standard deviation, then 68% of them would be in that gap of 1 standard deviation above or below the mean. Most people would be in that general middle kind of area. And you'll see how I've represented that as there's a 34% here and a 34% here. I've said it's 34.1 and 34.1 because that's the most accurate version, but you just need to know it as 68. The next layer, if you add in another standard deviation on either side, is that total probability is 95%. And if you add on another standard deviation either side of that, you get 99.7%. So if you do another standard deviation of that, you basically get everyone. Okay? If you do another standard deviation of that, you basically get, it's so close to 100% that there's not much point in kind of thinking about that. Okay? So really, what we're saying here is most of the data lies between mu minus 3 sigma and mu plus 3 sigma. And what I've said down here is for practical purposes, if we just go all the way 5 standard deviations above and 5 standard deviations below, the area underneath that curve is basically 1. Okay, we don't actually need to worry about going to those small bits because they're just so close to the axis. And all this is just a histogram above, which is for a quantity which is approximately normally distributed. So instead of doing a curve here, I've done them as like these different bars instead. Okay? So you have to know it, 68, 95, and 99.7. I'm going to do a quick couple of these to think about, and we're going to start using these facts that have got nothing to do with the calculator. I don't want you to use a calculator for this stage because we're trying to test those things that we've just done. The diameters of a rivet, there's a picture of a rivet up there, produced by a particular machine, x millimeters, is modelled as x is distributed normally with a mean of 8 and a standard deviation of 0.2, or a variance of 0.2 squared. And we're trying to find out the probability that x is bigger than 8. And this is actually how machines make things. If you collect a lot of things from a machine that has been made, There will be some things that are made bigger and some things that are made smaller, and they do actually fit a normal distribution. This is just how the world works. It's kind of fascinating when you start thinking about it. So we draw a quick sketch of what the diagram looks like. The diagram is just going to be, and you need to try and get into the habit of drawing this kind of shape. This kind of rises up and rises down, okay? What did we say goes at the center? So the center is going to be here, 8, because this is what the mean is. We're trying to find out, for part A, the probability that the rivet has a millimeter which is larger than 8, which is this area that we have over here, which is? No. I haven't, nothing, it's just 0.5.
Yeah.
The whole thing is 1, and it's half of it, okay? The second part says, what is the probability that the rivet is in between 7.8, here's going to be 7.8, there's 8, and 8.2.
40%, 0.4.
No. What do you notice about this gap and this gap? First of all, they're equal to each other. Okay, what is the gap? 0.2. What is 0.2 in relation to the distribution? Look back at the distribution. Good. Here, the standard deviation is 0.2. So we've gone 1 standard deviation above and 1 standard deviation below. How much data is in between 1 standard deviation above and below? 68%.
68.
Look. It says 68% of the data is within 1 standard deviation of the mean.
How do you remember that?
So now we're actually using it, okay?
It's within one
Is within 1 standard deviation. Yep. And so you could use that. If I then said, I'm going to add in a bonus question. If I said, what is the probability that, let's try this instead. What is the probability that x is greater than 8.2? So I'm going to draw a diagram now. And I want to see if anyone's smart enough to think what this is. So yeah, there's many different ways of thinking about this. If we know that this thing over here is 0.5, because it's a half of it, what would this area here be?
Half of the 0.34.
Good. These chunks together were 68%. So one of those chunks must be 0.34.
Therefore, 0.16.
So it would be 1 take away 0.34, take away 0.5, which is 0.16. I'm sorry, Hamza, you said that and I just ignored
I
you.
knew you were waiting to do that. Right?
So the information that I've given you here is richer than it looks. Do you understand what I mean by it's richer than it looks? You can use it to find out other things as well, okay? Yes?
So, if you, how am I going to work this?
Why is it squared? What?
Come back to me when you're
Let's say
yeah.
Let's say you were slightly more to. So you see how the diagram above them.
Yep.
So these 0.16.
Let's say we shifted those two lines a little bit to that side.
Yeah, it's going to change completely.
Okay.
Sir,
It's going to completely change, so we can't do it. We'll use calculators for that, okay? Yes?
why is it always squared?
That's just how we write it.
Okay, so it feels like 0.3 squared, and then the gaps for 0.3, then you would say that is the 0.68.
Yes, if it said this, what is the value of the standard deviation?
20th of 0.68.
Pardon? You square root it. You would do the square root of 0.01, which is, come on, 0.1. So actually, the standard deviation in this one is 0.1. So if they tell you it and it's already squared, you can just ignore the square. If they tell you it and it's not got the squared, you have to square root it. It's just annoying. It's just what we do. It's the variance is what we write instead, rather than the standard deviation. Okay? So that's a couple of examples. I'll do another one. IQ. This is how you've heard of people talk about IQ, right? Like, what's your IQ? What's your intelligent quotient? And this is actually, I'll just show you this. This is actually how it's defined, okay? The IQ is defined that the average score is 100, and 68% of people are within one standard deviation, and the standard deviation is 15. That's how they set it for the test. 95% of people are within 2 standard deviations. If you go outside of those 2 standard deviations, there's either an indication of being gifted or an indication of some kind of developmental or learning disability. So this is actually how normal distributions are used in real life, okay? They are used to set things like test scores. They are used to set things like IQ and to decide whether somebody needs additional support or whether someone needs to have additional education, okay? So I'm going to do the same thing. I'm going to draw a diagram. I want you to be in the habit of drawing a diagram. I want to find out that the probability is between, 70 and 130. So quick sketch, doesn't need to be perfect. 100 is in the middle. And I'm going all the way up to 130 and all the way down to 70. What's this gap in terms of the standard deviation? It's 2 standard deviations. It's 2 sigma. And that way is also a 2 sigma gap. How much? Because one of the standard deviations is 15, and it's going up 30. Good. So it's 95%. Okay? It's 95%. Now, actually, if you want to, and you know how to use your calculator, you could put in 100 as the mean, 15 as the standard deviation. You could put in 70 as the lower and 130 as the upper, and it will give you not exactly 0.95, I don't think. It might do. Let's have a quick look, actually. So I'm just going to quickly try this out on my calculator. Not this page. So the lower was 70, the upper was 130, the standard deviation was 15, and the mean was 100. So it doesn't give you exactly 95%, but you can see it's basically 95%. Okay, so that's what it is on the calculator version. We've just done it, though, like this. Okay, let's have a quick look at one last thing before you do a tiny bit of practice. We're now going to say, what is the probability that someone's IQ is bigger than 115? So again, we draw a diagram. We look at the normal distribution here. There's 100, always put that in. There's 115. What do we notice about 100 and 115? One standard deviation. So this is one standard deviation. So in between of them is 68%. So 1/2 of it is half of that, which is 0.34. Because if there was another bit there, it would be 68. Half of that is 34%.
But you want that little bit at the end of it.
We want this whole bit as well. So this whole bit together, do you know what this whole bit here is? Yes, you do. You know what this whole section is here. It's 0.5. It's the whole thing together, okay? So the probability that something is bigger than that, I actually think we did a question like this just now, didn't we? The probability it's less than that is 0.84. So it would be 1 minus 0.5 minus 0.34, which is 0.16, which is, I think, actually the question we just did on the previous page, okay? So you're just going to draw. I don't want you to use your calculators. You can use them to check them if you want to. But the basic idea of what you're going to be doing for me in these questions is you're just going to be using the knowledge that you have from so far. And I just want you to do it on this page here. There's just 3 questions for you to have a very quick go at. I'm going to give you like 3 minutes to do these, and I'll leave it on that page, okay? So you've got 3 minutes to do those.